Okay, so here we are starting part C. We want to plot our Bode diagram. And I'm actually going to combine C1 and CB, 1A and 1B with this. So I'm going to plot these and then I'm going to determine the amplitude ratio from that. So I am going to go over. Okay, so then we're going to come here to our Python, and I'm going to start with our Bode plot and it's going to be in terms of W, dB, phase, and then this is equal to sig dot Bode and transfer function forward. And then next I'm gonna do fig equals make rows equals 2 and I think this just needs to be row equals. Then we'll do fig dot add where t is equal to w. Oh, I don't know why I said t. X is equal to w. Y is equal to dB. This will be equals is equal to dB. Then I'll just copy this whole thing. And this will be equal to, and then our row 2, this will be named phase. We also want this to be exponential on the bottom. This is going to be type or do big dot update layout, and this is just going to be width equal to, I don't know, 600. This is going to be too much. I need to fix this. And then height equal, I don't need these, I keep doing that. And height equal to 800. I think that's going to be too much, but we'll see what this does. I think these need to have S's. Okay, perfect. It's a little big, but so this is the Bode diagram, and this is our dB, and this is our phase. Okay, now to compare the amplitude ratio against our result from our part B2. All I need to do is convert to our amplitude ratio, and to do that we need to do 10 to the power of dB divided by 20, and this needs to be 1 with W equal to 1. I'm just ask what AR is. And that gives us 0.6403. So then we can come back up here and we'll go to our H2 plot. superimposed one, and go to the top of these plots, and it is 0.634. Basically the same. The reason it is not exact is we just don't have enough plots. If this would be, we'll try that. That might be too much. We're getting closer to 0.64. So that is how it compares to B to C. Okay, so now for part to explain the concepts of crossover frequency, phase margin, and how this relates to the stability of the system under feedback control. So I'll go back to my my plot here. So we go back to our Bode diagram. And what we do, so first of all, crossover frequency is basically just where this phase portion of the diagram crosses this 180 mark right here, where it's 180 degrees. So we see here that it's crossing over here just a little above 1. So what I'm going to do, so it's about 1.14, where it seems like it's 1.15 is where it's crossing over. So I'm going to go up here to 1.14, it's about right here. So it's negative, and it's below 0, which means that you're stable. And what we also want to talk about too is our phase margin. And so to know, phase margin is basically just knowing how many degrees away are we from being unstable and this feedback loop being no good anymore. So what we can do there is we can go to 0. Let me get to 0. Okay, that's pretty much 0. So we're at 0.81. So I go down here and I go to 0.81, and we're at about negative 173 degrees. So we're about 7 degrees, or if we want to round up, 10 degrees away from being unstable. And that is what crossover frequency and phase margin mean and how it relates to stability. Okay, so now if we want to put Kc at equal to 3, and see how this changes the stability of our feedback controller. So we have, we'll put this equal to 3, go through all these. To our frequency, that calls, sorry, crossover frequency. I was trying to say over cross frequency. Crossover frequency, and it looks to be about right here at this 1.149. So we'll go up here to this 1.149, and you can already tell that it is above 0. So it being above 0, it has no phase margin, and it is unstable and above 0. So it will have a lot of difficulties, and it just cannot be done. So now for this last part of part C of homework 4, graph for part B, A. And as you can see, this is stable. This is at a Kc of 1, and as we can see, this is stable. It starts kind of unstable with these large lines, and then it slowly decreases. And if we eventually zoomed out enough, well, if we had enough plots, it would come out to almost a straight line. So it shows that it's stable and it's going to stability. Now, if we change this to 3, this shows that it starts kind of crazy and it just keeps getting crazier, and it just won't ever find a stable ground. It won't find this number that it finds at its stability. So it just keeps getting crazier and crazier, and you'll just get this huge graph and it'll never stop. And so this proves that a Kc value of 3 in this particular set of transfer functions is unstable.